Welcome once again to the running of this course. I hope you are enjoying it. I am trying to give it as slowly as possible, keeping the variation in the audience. So, today we are going to talk about derivatives of many variables. So, you may wonder that once we have spoken about partial derivatives, why do I require to speak about derivatives of functions of many variables? I could say, okay, that partial derivative means the derivatives, that is all. So, I do not care about anything else. See, the idea of getting the derivative of functions of two variables or many variables took mathematicians many years to formalize and make the idea look consistent, look all right. The key idea, if you look at the derivatives, is that if you just take a function phi from R to R, then if phi is differentiable at a point x naught, differentiable at x naught in R, then phi is continuous there. This is a very fundamental fact. So, existence of a derivative at a given point guarantees continuity of the function at that point. The reason that we need to talk about functions, derivatives of many variables separately and not just consider partial derivatives is precisely the fact that there can be a situation where the function is discontinuous at a given point, yet the partial derivative exists. So, if you look at this statement, what it says, differentiability implies continuity, no continuity at a given point implies no differentiability. So, it is very important that can we define a kind of derivative, right, and for functions of many variables which would make the function continuous at a given point. So, now look, let me clarify that the partial derivative exists while the function itself is discontinuous at a given point. Define this function f of x y, where x is in R and y is in R, function of two variables, and this is defined as follows. It is equal to, this is a definition from the book, this is an example from this book itself. So, I will just write down the exact example. So, it is 1 if x is equal to 0 or y equal to 0, means also at the origin it is 1 and 0 otherwise. So, if you draw the x axis, the y axis, and this is the point 0 0. So, along the x axis and y axis the function has value 1, the graph is like this, while is 0 otherwise. So, it does have a discontinuity at the axes and hence at 0 0. So, suppose I want to calculate the del f of del x at 0 0. So, instead of writing like this, I will start writing it like this, it is much more easier, del f del x at 0 0. So, how do I calculate del f del x at 0 0 is limit h tends to 0, f of 0 plus h 0 minus f 0 0 divided by h. Now, what is f of 0 plus h? So, what you are going to have here, limit h tends to 0, f of h 0 minus f of 0 0 by h. Now, we have said that if either of x or y is 0, the function value is 1. So, this f h 0 is 1 and f 0, this f h 0 that you see here is 1 and f 0 0 is also 1. So, the limit becomes 0, 1 minus 1 0, so it is 0. So, the partial derivative at x exists. Similarly, you can compute that del f del y at 0 0 is also 0. I will leave that computation to you. So, you have this as well as you have this fact. So, the partial derivative exists, very simple example, at the point 0 0 and the values are 0, but the function itself is not continuous. The function is not continuous. See, in mathematics you might say, why you need to do some certain thing like that, why you need to be worried about this issue when you come to higher dimension. You see, in mathematics the progress is done in the following way, that once you have built a very basic theory like that of calculus of one real variables, then when you build theories in higher dimension, you want to mimic properties of one dimension in higher dimension, and you think that if those properties are carried over to higher dimension, your naturalization is general. That is the way of thinking that pervades all of mathematics, that okay, if I am trying to generalize something to higher dimensions, the most important and elegant properties must carry over to higher dimensions. Of course, there will be certain properties which would be very intrinsic to this thing, which will not carry over to higher dimensions, but the most elegant properties which would appear to be free of any additional structures have to have that property that it is being carried over to the higher dimension, that can be carried over. So, and what should be the definition of the derivative of a function? Suppose I take a function now f from Rn to R. Now, my question is how to define the derivative? How to define the derivative so that a differentiable function is necessarily continuous, not which means necessarily continuous. Sometimes you might find the language of math becoming very. So, how do I do it? Let me show you how to do it. There are two ways, one is the geometric way, one is the intuitive way. So, we will use first my intuitive way, which I like very much, and then we will go to the geometric way. So, if you go to the definition of function, suppose I have a function phi from R to R, and then I want to talk about the derivative. So, derivative at a given point x naught that limit of h going to 0 phi of x naught plus h minus phi of x naught by h, this is 0 and this limit should exist, and suppose this limit exists. Now, what happens? What happens is the following, you know that if I write limit of h tends to 0 phi dash x naught, it will become phi dash x naught because this is just a number. So, I can write this in a slightly different way. So, this would imply that limit h tends to 0 phi of x naught plus h minus phi of x naught by h minus phi dash x naught is 0, because if you take the limit here, this limit would be phi dash x naught, and this, because it is constant, its limit would be, this will be also limit would be phi dash x naught. So, they will cancel up and give 0. It is just a rearrangement. Now, this also implies that limit h tends to 0, phi of x naught plus h minus phi of x naught minus phi dash x naught h divided by h, that goes to 0. Now, what does it say? What does this story tell me? This story tells me something else. It tells me, which I will write on this side now, because I am sure that you have noted down what I have done. So, what does this tell? This tells us that h is also going to 0, but there is a numerator and their ratio is also going to 0, which means that the numerator must be going to 0 faster than h, otherwise it will blow up. So, if the numerator goes to 0 faster than h, then we say that the numerator is a small o of h quantity. So, what is this? This is a function of h, because x naught is fixed, this is a function of h, and this function divided by h is going to 0. So, this function goes to 0 faster than h. So, we define something called O of h. So, O of h is a function, small o of h, of h. So, this is a function which satisfies this property OH by h as limit h tends to 0 is equal to 0. As an example I am giving you, OH is say h square, right, h square, because observe that OH by h is equal to h, and this goes to 0 as h goes to 0. So, this is very, very clear that why that it is not very difficult to construct OH of functions which vanishes to runs to 0 faster than h. See what happens, look at just this function. So, h square is smaller than h when h is very near 0, and that is why it is going to 0 faster. You just look at the graph of y equal to x square. So, now, so by the definition of a small OH, what do I get? I get that phi of x0 plus h minus phi of x0 minus phi dash x0 h is a small o of h quantity. That is what I get from this definition of small o of h. So, this quantity must be a small o of h quantity. So, this implies I can write the derivative can be now defined as a number which satisfies this condition. What does it say? That as the error, as h goes to 0, the error that you have between this and the this is the kind of error. So, this phi x naught plus h is equal to phi x naught plus phi dash x naught h. This is actually, if I forget this line actually is the tangent at x naught phi x naught. What we are telling that when suppose h is very small, then functional value at x naught plus h can be very well approximated by this tangent line. Basically it tells you this fact. So, this is if this is x naught phi x naught, then if you take the tangent line, So, if you are very near, so if you magnify this zone, so if you are very near x naught, this point, then your tangent line value and the value of the function does not differ much, the error is less. So, as you move towards this point, the error becomes smaller and smaller, that is exactly what it says. So, now how can I use this idea, this thing that I have written, can I consider this as the definition of the derivative? Yes. Now, if I consider this as the definition of the derivative, I need to go ahead and define the definition of the derivative in that fashion. What I will try to do is I will try to define the derivative in this fashion. Let me see how does it work. Now, I will say take a function f from Rn to R, and let x0 be a given point. So, this is with this premise I am trying to define the derivative at the given point. So, here I will keep it, it will write it down so that you have it throughout. So, f is from Rn to R and x naught element of Rn is given. We say that f is differentiable at x naught if differentiable at x naught if the limit of norm h tending to 0 now h is now a vector, it is a vector variation, right. You move from x naught from one vector and you move along the direction of the vector h. So, here you have x naught, I am just looking at in R2, here you have x naught and you move in this direction, this is x, if this is your h. So, you move in the direction x and come here at x naught plus h, right. So, this is what you have. Now, f of x naught plus h minus f of x naught. So, what is the derivative? So, let me now write down, if this is a sign of there exists in mathematics, if there exists a vector v such that limit of v dot product h, you know multiplication, here I was multiplying the derivative with h, here the derivative is multiplied with h, but now when I come to higher dimension the notion of multiplication gets changed to dot product, which is the most natural generalization. So, we put the dot product. So, it is a kind of intuitive step that we are taking, though it is not kind of rigorous way of defining things, just we are telling the what, we are trying to look at that definition, that rearrangement, and then we are trying to play it out here. This divided by norm of h, this limit should be 0. So, we say that a function is differentiable if you can find a vector v for which this is true. You can also write it like this, a vector x tending to x naught f of x minus f of x naught minus v dot x minus x naught, h is now x minus x naught. Basically, you are putting x naught plus h is some x. So, norm is, this is norm x minus x naught. That is another way of defining it. a very general way of writing the notion of a derivative, or symbolically the derivative is written as V is d of f of x at df at x naught, the derivative V is the derivative at x naught. So, you can write V x naught, I am just writing it because you know that V is only for x naught here. Now, if you know that the derivative exists, you can show that this is nothing but the following vector, which has as its components the partial derivatives. So, the derivative consists of a vector. If it exists, if such a vector exists, then it must be the vector of partial derivatives. So, this vector is sometimes also called the gradient vector of f at x naught. Now, if I have a function from Rn to R, f is a function from Rn to R and differentiable at x naught, that is the derivative exists, then is it continuous? That is my question. Then is it continuous? The answer, yes. So, you ask how, and let me show you that how. So, we have to show that limit of f of x as x tends to x naught must be f x 0 for f to be continuous at 0. This is what we have to show. This is to show. So, let me just start with computing this limit. Limit f of x, x going to x naught, limit x tends to x naught, f of x minus f of x naught plus f of x naught is equal to limit x tends to x naught, f of x minus f of x naught minus d f of x naught dot product x minus x naught plus df. So, you are adding and subtracting this term dot product x minus x naught plus f of x 0. So, then you write limit x tends to x naught, f of x minus f of x naught minus d f of x naught dot x minus x naught divide by norm x minus x naught, because x is not equal to x naught. So, you are multiplying and dividing and multiplying x naught plus df of x naught dot x minus x naught plus f of x naught. Now, you can understand when you take the limit, this one becomes the derivative, which is just a fixed vector. Because of the definition of the derivative, when you run the limit, this limit is 0 and this limit is also 0 because x goes to x naught. So, this both the limits would be equal to both the limits, this is 0 and this is 0. So, this whole product is 0 plus here as x goes to x naught, this will become 0, and because inner product itself is a continuous function of x, it is actually a linear function if you look at it very carefully. So, this will go to 0 and what we have left with is this constant f x naught. So, this is f x naught and voila, we are through. as the French would say, voila, we are done. So, which means that we have actually defined the derivative in a way which maintains the main question that okay, if I have a differential function, if it is a function, if the function from Rn to R is differentiable at x naught, then is it continuous at x naught? The answer is yes. So, our definition does make sense. So, to keep in view of so much discussion, let us now consider a function f from Rn to Rm, because we were already talking about vector valued functions of vector valued variables. Means you are taking a many variable function which takes a vector and maps it to another vector, it does not map into a scalar. So, in general f can be thought to have n components. If I evaluated it at x, it has m components and each of them are viewed as functions. There are m functions from Rn to R. So, each fi is a function from Rn to R. This is something you have to remember. It is true for all I. Okay. Now, once I have done that, how do I define? Can I do the imitation of the definition we have for Rn to R? The answer is yes. But here the thing would be slightly different. The derivative will not be a vector, it will be a matrix. So, if x naught is element of Rn, we say that f is differentiable at x naught if there exists a m cross n matrix Jf x naught, we maintain the same sign such that limit x goes to x naught, the norm of, because now here the upper level is, see if you look at this, when look at this definition when we had used for a function from Rn to R, the top level is real number, the lower level is real number. So, we divided to real numbers, but there is nothing like dividing to vectors. So, what we have to define is in this form, that you have to take the norm of upper and lower level. So, capital F of x minus capital F of x naught minus j f x naught, this vector, this matrix multiplied with the vector x minus x naught norm of this, divided by the norm of x minus x naught. We have already learned about norm in the previous section. So, you see how useful those notions were, inner product and norm and all those things. This is 0. This mapping, this vector, this jfx naught is often called the Jacobian mapping. The Jacobian mapping or Jacobian matrix at x naught. And what are the elements of the Jacobian matrix? So, the Jacobian matrix at x naught consists of elements of this form, del of fi, del of xj. So, the ith jth element is of this form. So, I is running from 1 to m, and so where I is run from 1 to m and j runs from 1 to n. That is what we have learnt. So, this is the basic understanding of the notion of a derivative of functions of more than one variable. Now, For the remaining part, I will talk about the geometry. So, let us see geometrically can we think about functions of, from the geometrical idea can we get the definitions that we have got. If you look at the definition of geometric definition of the derivative of a function of one real variable, the geometric definition is that it is the slope of the tangent at the point where you are computing the derivative. So, if you are computing the derivative at, say, this is phi x, this is phi x, and suppose you are computing the derivative at this is x naught and this is x naught phi x naught. So, you are computing the derivative at x naught, and the slope of the tangent, this one, this is the slope. If this is theta, then tan of theta, then sorry if I write it here, then tan of theta is phi dash of x naught. That is the interpretation, that is the meaning of the derivative. But how do I put this idea into work when I am in higher dimensions? So, let us look at a function z equal to fxy, and let us try to imagine a curve, try to draw the surface, try to draw the graph. Let this be the surface, let it look like this. This is your z equal to fxy. Now, take a point x naught y naught, z naught. So, this is x naught y naught 0, and this is a point x naught y naught and some z naught, where z naught is of course f of x naught y naught. Now, you fix your x naught, this is the x naught, and what you get, basically you are drawing a plane which is cutting perpendicularly the xy plane and passing through x naught. It is kind of a plane like this. Let me just draw the plane in a different color. So, the plane is passing through it is cutting. Similarly, I can think of a plane which will make y naught fixed and is cutting the xy plane in a perpendicular way while passing through the point y naught. So, basically I can think of a kind of curve. So, the slope of the tangent, right, the slope of the tangent, so slope of this line when x naught is fixed, slope of the green curve, slope of green curve is nothing but the del f of y evaluated at x naught y naught, because here x naught is kept fixed. Slope of the maroon curve, slope of the maroon curve is equal to del f del x evaluated at x naught y naught. So, here is a geometrical explanation, of the partial derivatives. Now, how far we can take the geometrical explanation? Suppose now we draw a tangent plane passing through x naught y naught, that is, you imagine something like this, the z axis, the x axis, the y axis. So, if you think of a tangent plane at this point, at the point x naught, y naught, z naught, then the tangent lines passing through x naught, y naught, z naught, which are actually tangents to the curve, green curve and the maroon curve, then the slopes of the green curve and the maroon curve and these tangent lines would coincide. This is a very reasonable geometrical fact, it just you can visualize this. So, now what is the expression of a tangent plane? What is the expression of a plane passing through the points, tangent plane passing through the point x naught, y naught, z naught, where z naught is f of x naught, y naught, right. This is something. So, any tangent plane could be given as follows. So, not tangent plane, any plane. So, any plane which is a tangent plane in this case, any plane passing through x naught, y naught, z naught will have an expression z equal to z naught plus a x minus x naught plus b y minus y naught. Now, z naught is nothing but f of x naught, y naught, that you know. The z naught is the x naught, y naught, z naught is a point lying on the surface. What is a and b? That is what we have to find out. Let us call this function as g of x y. What we said that the slope of these functions along the x direction and the slope along the x direction and y direction, that is the partial derivatives of this function at x and the partial derivative of the given function f at x naught, y naught should match, that is del g del x at x naught, y naught, which is a, should match del f del x at x naught, y naught. Similarly, del g del y at x naught, y naught should match del f del y at x naught, y naught. So, the tangent line can now be expressed. So, the tangent line can be expressed as z equal to z naught is f x naught, y naught plus del f x at x naught, y naught. So, here a that you see here, this what I write here is a dot product, that I just wanted to let you know. So, dot product with x minus x naught plus del f del y dot y minus y naught. Now you see, if you want to define the derivative, so this is a linear approximation which says, so the value of the tangent when the distance between x and x naught and y naught, it is very less, between xy and x naught y naught is very less, then the value of the tangent is very well approximates f of x and f of y. So in general I can write f of x of y is f of x naught y naught plus del f del x x naught y naught dot x minus x naught plus del f del y at x naught y naught. See, these are all evaluated at x naught y naught. See, all the vectors etc. that we have done here before, everything here is evaluated at x naught y naught. See, here it is x naught, the vector x to r n basically. So we are just doing it for two variables. See, when I am doing the geometry, I am just doing the geometry for two variables, right. So I am just trying to explain you in terms of two variables. This y minus y naught plus error. And how should be that error? That is the question. That error should be in the following form. That error term should be that when x is x going to x naught and y is going to y naught, the norm xy is going to, when xy is going to x naught y naught, then this error term should vanish very fast, right. So, it is a kind of error term in general should be a small o quantity of norm of xy minus x naught y naught. That kind of quantity should be the error. So, you see, if you look at this, so if what I do, if I take fxy minus fx naught y naught minus this thing, so if I look at this thing, sorry, this is not a dot product, this is just x minus x naught. I am making a mistake because this is x is just two variables. So no, I am making a mistake. Please have a look. This is just a real number a into x minus x naught, real number b into y minus y naught. X y is the vector, x and y are real numbers. So these are not dot products, right? These are just y into y naught. This is this into, so y, x and y, these are not vectors. So I am confusing. I am just thinking as if I am writing in higher dimension, which I am so habituated to. So these x minus x naught and y minus y naught are real numbers because we are in two dimensions. So x is a real number, y is a real number forming the coordinate xy. So here if you look at this, what I have fxy, if I write like this, I can write minus fx naught y naught minus, if I look at this thing, it is a vector del f del x x naught y naught del f del y, which is nothing but the gradient vector x naught y naught, inner product with the vector x minus x naught y minus y naught. That is exactly the definition, and this is nothing but a O of norm xy minus x naught y naught. So you see, from the basic geometry of the tangent, when the tangent line is a very good approximation to the function value for all xy near the point x, all xy values near the point x naught y naught. So that with that idea, you see, we are bringing, we get back the same definition of the derivative which we have got intuitively by doing certain algebra on functions of one variable. So with this very simple geometrical approach, this gives us exactly how a derivative should look like. In two dimension we get, so both the cases we get back the same form of the derivative, which is the gradient vector, and thus this gives us a very meaningful way of doing the things. And with this idea now we can proceed further, which will come, we will talk about chain rules for partial derivatives in the next class, as well as we will talk about many other things as we go on. We will gradually get into deeper issues like gradients and directional derivatives and the relation between directional derivatives and the gradients, and also about implicit function theorems and all such things. So, we are gradually getting deep into calculus of function of many variables. You see, so this is a very interesting thing, how geometrical thing can come and match with the intuition that you already had, from which you defined a derivative, and you said that the definition of the derivative what we made was very good, because we could prove that with that definition of the derivative, if a function is differentiable at a given point, it is continuous at that point. So, you see that we have been able to maintain this very important property, and hence why what we did is meaningful. Thank you very much, hoping to see you in the next class.